me from my favorite artist, electronist, Mr. Q12. I was watching a couple of weeks or even months ago. Some guy on YouTube. Was building this circuit here. This is actually a screenshot from his movie from YouTube of the circuit diagram. I've put myself here a correction to actually see it better. 4313 is the flip-flop integrated circuit that he is using, and also a NAND gate here, 4011. This guy here, and this is the original circuit. Here is how it looks. So two flip-flops and one NAND gate, and only one gate is used. It's a waste of chip, in my opinion. But this is the idea. This was the project. It was a kit from China, and I really thought it is a very good teaching example for teaching myself more a little bit about logic ICs. Here is its page, and you can watch it if you like. But it's the same thing that you just see in my screenshots. And so after watching that movie, actually it passed some time before I actually started to make the circuit here in a simulator and in reality. I had other circuits on the table at the time, but I remember this one to try it out, and finally I got the time to try it. To be very clear, this was simply a fun circuit project. It wasn't really something serious. I don't really think this is a serious circuit. It is in some way, but not serious for me, at least from my perspective. It's kind of good. It's okay. It's not bad, not good. It's somewhere in the middle, in the silver line. So here it is in Proteus. So let me actually make it full screen and run it. And this is the behavior. We'll look here on these pins 1 here where it says Q 1 and the 13. So let me actually make it very clear here and here. This square, blue square here and this blue square, they will toggle between red and blue. And pay attention to those for each of them. This is the first chip that is having only 2 gates or 2 flip-flops in it. And it's 4013. I don't have this circuit in my arsenal of circuits, of integrated circuits, but I simulated his circuit, the guy who made the movie, and it's working. First of all, that's the good thing. But we will discuss the problems when we will reach them. And when I'm clicking this clocking switch S, this S1, S2, S3, it means switch, stands for switch. So when I click this switch here, if I'm resetting, pay attention again. These two actually, they will toggle between them. One is output and not output. This will be the output is the inverse of the output. And if here I'm having negative like it is right now, here is positive. Red is positive, blue is negative. And when this will switch the positive, the Q, the not will switch to blue. And that's the way it works. But it doesn't matter. What we are concentrated on is only this normal output, the Q1. That's what is important here. So when I click it here, it changed there. The input is getting 5 volts here on the first. Actually, let me show you my IC 4013. I don't have it because I don't have it. No, I don't have it. But I have its datasheet. Very weird. No, I wanted to show you 7474 there. 7474. So this is how it's looking inside. It's having at least my circuit, my integrated circuit, but it's the same with 4013 as well. It's having literally it's having 2 on one side, one flip-flop on one side and another flip-flop on another side. That's it. This is the case with these 2 squares that we have here. So one D flip-flop on one side is getting 5 volts. When it's toggling this output to positive, it's actually flipping to 5 volts, from 0 volts to 5 volts, and then this is activated, the second one. So that's when I'm clocking it in. You see every clock pin are on negative. And when I'm clocking it here is activating the third one, the third clock, which is contained in the second chip. Or I see when I'm clocking the third one is activating the fourth flip-flop from the same second chip. And this is the magic. When I'm pressing this switch here, it happened a lot of stuff actually in a very brief time, in a very short time. And but when I first see it, I had to run it a couple of times and I still didn't get it. And then after a while playing with it and demystifying it, I started to understand it a little bit better. What just happened when I clicked this last clock here, the current got through this NAND gate. So if I'm doing right now like this, you see it's activated with positive here and inverse this NAND gate inverse to negative and reset every flip-flop except the last one. As you can see, let me close this. As you see, this output of the NAND gate is linked only to the reset of these 3 flip-flops, but not the fourth one. The fourth one is having a separated reset switch here, and also I cannot say separated the clock because the clock is separated to each of them. The clock switch or button earlier. So this is an automatic reset. This NAND gate is used as an automatic reset for these other 3 flip-flops when the not Q here is activated. But I didn't, and I was very happy when I built it, the original circuit. It was working. It's very, very cool. But I didn't notice the problems here in the simulator. I mean, it is working for what it is. It's okay. If you are willing to get over some issues that it's having, close your eyes. for me, like I'm saying, it is a fun project, first of all. But even if it's a fun project, I still want the best and the best thing. And it was kind of annoying, the stuff that I uh, let me actually show it here in the simulator, and then I will show it in reality. So here, if we are setting the first flip-flop and the second, and if I'm pressing one reset button from all this here, 1, 2, 3, 4, 5, so these 5 reset buttons that I'm having only on this side. So let me make it like this. So this is the first side of the circuit, like this. Okay, this first side. The second side is this here, which is dealing with the automatic command of the first module here, the 3 flip-flops. So if I'm resetting, it doesn't matter which button I'm pressing, you see all those outputs are reset to negative, to 0 volts, or to 0 logic. And I have to start again. And now I'm having all these 3 activated. But before I'm pressing this, I will still press randomly this guy, and everything was reset again. So everything is working in this sector. That's it. This is all that is doing, this module of 3. So let me draw it again for you. This module of 3 flip-flops, that's all that is doing, is setting and resetting the flip-flops. It's like a cascading, one after another. And when I'm activating this guy here, you see it did push to positive line. It put to positive every reset that is on the first module here, and everything was reset. In the moment this reset pin was on the positive here from the NAND gate coming through. Here in the simulator, it worked with 10 kilo originally. This is the original circuit that they are having there, and on the circuit schematic. And it's very weird. It did work here in Proteus as well. Is working like this, but this resistor is very important. It must be under 1 kilo, not 1 kilo, but less than 1 kilo, for everything to function properly. If it's too high, it will conflict with other logic that is having here. But for some reason here, it's working fine with 10 kilo, and that's how the original diagram was. Let me check, not this one. So this here, this is the original diagram. This is the 10 kilo here. This is the guy. And they show it here, but it's not really. No, it's not correct. It's not correct. It's working, but it's not correct. It should be less resistance. Okay. I want to show you right now the issues that I'm having with this circuit. So I press this button here, but when I'm pressing right now again, you see what is happening. The same S9, the same switch that I'm activating the 4th flip-flop is activating. So the first click on the button is activating the LED. When I'm first clicking it, the automatic resetting for all of these 3 flip-flops is activated. I'll reset to 0. As I was switching before on this manual button here, is the same thing, but automatically through this NAND gate here. And that's from the first click on S9 here, on this switch, from this clock switch. But when I'm switching again, it's switching off this LED as well, which is not really a big issue. But if you see the how it's working, how everything is working. So the general functionality of the circuit is like this: switch 1, switch 4, and if I'm pressing also on switch 4 or switch 1, and if I'm pressing S7 is activating this one. But if I'm pressing every switch here, the clock switch, nothing is changing, nothing is changing, nothing is clocking, is remaining on the positive here. If I have to put an LED, and in reality in my circuit board, in my breadboard, I did put an LED to each output here to actually see the signal exactly like we are seeing here on the Q output, this square, exactly like that. This is an equivalent with a LED in reality. But if I'm switching all these clocks, if I'm clicking all the buttons only on the clocks, everything remains positive, not changing at all. But this little fucker here, it is switching on and off, and also switching the not Q as well. These two are linked together in an opposite manner. So if I'm switching now, is resetting everything and leaving the output on. But if I'm pressing it again, you see this one is not changing anything, was not changing anything on its output, neither this one. But now when I'm pressing this one, it is changing, and that's very weird, because we have a reset pin here designated for resetting, and this little shit, this little detail annoyed me, kind of annoyed me. It is perfectly usable as it is. You have pretty much 2 reset pins or 2 reset buttons, but in reality it happened something bad a couple of times, multiple times actually. When I clicked once, the button bounced a little bit. Let me actually find you a bounce diagram to see exactly what I mean. This is how this bouncing is. When I press the button, is doing a little bit of up and down, nearly to 5 volts, or even the maximum. A couple of times here are only 1, 2, but in reality there are probably a couple of tens. Like, depends on the button, probably 10 or 20 little spikes like this. So this is how it's bouncing a couple of times, not only 1, 2 times. But you see, and it's lowering down the value, and this is a very good button that is bouncing like this. There are worse buttons that are doing a lot of nasty bouncing inside. So that's what this S9 is doing. So you see my problem. This was very, very important thing. So if I'm activating every flip-flop again right now, and if I'm pressing this 2 times, is letting the output staying on for a very brief time, and then is resetting back to 0 everything. And doesn't matter how many times it's bouncing after that. Doesn't matter, because everything is reset, and the output is not staying on. You cannot open anything with it. You have to be to have a little bit of luck to press once and that output to stay activated and not bounce, and somehow to avoid the bouncing of the button and not reset everything to 0. So you see my problem. That's what I'm sorry I had to explain it so much, but it was an important detail, and they are relying a little bit on luck, which I really don't like it. I want a circuit, especially a logic circuit, to be logical, to be either 1 or either 0, but nothing in between. Not if it will work. No, not like that. Electronic is not if it will work. Electronics is about you are working, motherfucker, or you are not working, motherfucker. And if you are not working, motherfucker, you have to find the problem. That's it. That's all the electronics in a nutshell. you find the problem, you resolve the problem, and that's it. And the circuit should work correctly. All right, here are on my table, not mine. That I just opened my variable power supply unit, 5 volts. It says there exactly 5 volts, not less. And the circuit is staying off, but it's good that it's staying off. This first button is the reset. It's the same circuit that you've seen in Proteus. I printed out this time. I didn't put this actually I did put this capacitor, but I didn't put that resistor there. And here I had to lower. It's not working with 1 kilo. It's not. It is working with 700 ohms, but what I did, I put 2 of them in parallel. I hope you can see, and they are 500 ohms, even lower than in the circuit here. And let me demonstrate it. So if I'm pressing this, I put an LED to all of the outputs. I didn't draw them the circuit, but I should actually for you to understand what is going on. So here is the LED that is pointing towards the negative. Yeah, and the same is for all, exactly like here. So exactly like here, I put on all this. You see here to ground, and here another one to ground, and that's it. 1, 2, 3, 4. And the last one is this red one. I only have 4 LEDs here, right? So if I'm pressing the reset, is functioning. If I'm pressing the first clock switch, I kind of minimized the circuit on the breadboard. I didn't put all this shit, all the parallel reset buttons. I only put one single button for reset because everything else is in parallel and really doesn't matter. As you can see, it's a single line that is uniting every other button. They were 5. They are 5 buttons there for reset. 1, 2, 3, 4, 5. And I only put one for all 5 of them and link them together through this line here, some wires there. And I minimized a little bit the circuit here on the breadboard. But in reality, it will have. I will put either the same number of buttons like is here in the circuit, or even more, more reset buttons, like 3 per each reset, and it will be very hard to if you don't know the password, and it will be very hard to guess it. I hope so. But this is a more demonstrative a learning circuit more than anything. And let me reset it again. So I'm setting this clock, which is here. This guy here. Yes, 11 in this case. It says here. This is the second, third. If I'm pressing reset, it is resetting again. Like I said, I linked everything together on only one single button. That is the one that is in the margin here. So let's do it again. 1, 2, 3. When I'm clicking the fourth, it is maintaining by luck the fourth output on, but resetting everything else that is behind. This part is reset through this AND gate, this chip here, which is having 4 gates in it, and only one is used. And if you ask me if it is a waste of chip like this, using only one, and also a waste of space, why not? And then if I'm pressing the same switch, this is the switch for the fourth here. The same switch here is closing, switching off that LED, and also switching the entire thing. But I'm having another button here next to it. So this is the fourth switch, and this is the reset, which is this guy here, the reset for the last. And it should work only with one reset and not 2 reset buttons. This is annoying. I don't like it. So let's switch it again like that. And when I'm pressing this one, if I'm pressing the reset here, it's doing exactly the same thing as this clock button is here, but they are not linked the same. They are linked differently. This button is linked to the reset, and this other button is linked to the clock pin. So the wires are different wires, but they are doing exactly the same thing, which is not good. This is the problem. So for now, it worked fine when I press. But if I'm pressing in a special way, I'm not sure if I can. No, I cannot. I cannot simulate it right now. But it happened while I was playing here. I press it a little bit funky, Let me actually take out this, guys. They are doing and not doing. Sometimes when I'm pressing this fourth clock button here, even with this capacitors here, is still managing to. Yeah, you see. But they helped a little better. These capacitors helped. The original circuit says to put the capacitor on the input of the AND gate, but it's having no sense. At least for me, it's having no sense. The button will debounce multiple times, and it will reset here on the clock. Doesn't matter how much energy this capacitor will hold on the input. The proper way to put the capacitor is on the shit. Here it was. Here is the capacitor. Actually, I put it wrongly there. Sorry, this button. I put it here on this button, the clock button here. So I tested with multiple values, with 10, with 20 microfarads, with 100 microfarads. 100 microfarads is too slow, but it's not that slow. It's a little slower. 10 microfarads is good, but sometimes it's keeping the button is debouncing and overriding this capacitor a couple of times. So the best value somewhere in between the silver lining is somewhere around 20 microfarads, 20 to 50 probably. And I put to 10. These are 10 microfarads, both of them, and I put them in parallel over the button. Yeah. I've also checked the marking, the negative to be here on this orange link, which is going to the ground. The internal button structure is very simple. Inside this button is like this. So are 2 wires, very flat wires. It's connected like single wire. And when you press the button, you make the connection from this wire to this wire pretty much. And if you put positive here, and if you put negative here, you will make a short. But if you put on the diagonal, so in the diagonal like this, or like this, here, here, and here, the negative, it will work fine. So this is transmitting from one side to another. If I'm putting here the capacitors, is absolutely fine. Is as I was putting them here on this side. So it's good to know what is inside your components. And this helped a bit, but really the button was overriding them as well. Even this 220, but they give me more good results than anything else. Let me do it again with no capacitors there on the button. Hopefully, yeah, you see, I did, and is retaining something. Is what? Also is I don't know why it's lighting up, but it's doing some nasty business which it shouldn't. And this time it did it so quickly the red button didn't open. But sometimes I manage to actually make it make it work. No, it's impossible. And if I'm putting here it says 10 microfarads, but I'm having here a 20 microfarads that I put on the input. Let's put it on the input to the ground. Yeah, it does. Okay. It is. Yeah, it is good. It is good. But yeah, you see, it did. If you are pressing in a funky way, sometimes is. Yeah, you see, it override this capacitor as well. The same it does with my my other two capacitors here as well on the bottom. Well, for some reason it does. It does help here, but it's weird. The location is very weird here, to be sincere. Because if this is bouncing like a motherfucker, the output is not influencing anything, but this is influencing a lot. Very weird. Why is working like that? But it seems it does, for some very strange reason. It shouldn't. Yeah, it's kind of stable. So this is the circuit that worked. Like this here, this is the replica of the original pretty much. But what I failed to mention so far is that I tried to convert the original circuit diagram with my chips that I'm having. Okay, so this is the original circuit that I'm having here, and that I explained a lot of stuff over it. And let me go to here. I made a variant, a copy, and these are all my tests that I did. That's why I reached to version 7 here, because I tried a lot of stuff. This was version 1. The idea, the challenge, at least for me, for myself, was to build it with my own chips that I'm already having. And if I'm, like I said, I don't have this 4013 one chip, but I flip-flop IC. But I have a lot of other chips, also flip-flops, a little bit different, but the difference is not that great. It's a logic difference, but in principle, you should be able to work with every flip-flop. In principle, with every flip-flop, doesn't matter what number it is. This is a DTFF, D-type flip-flop, and also my 7474 is also a D-type. So I have, these are the two guys, okay? These are the two chips. This in the left here is the 74 that I have, and here is the 4013 that I don't have. And at the first glance, when you first look on them, you don't notice the differences. But after trying to make it work with my chip, with my 7474 that I have, I noticed that it's having an inverted reset here, and that matters. It does matter, this inverted reset, compared with this one that is not having an inverted reset, and also an inverted set here, but we are not using the set at all. And the rest are the same. The D is the same, the clock is the same, is not inverted, is absolutely the same as this one. But only that motherfucker reset is inverted. This means I must wire them a little bit differently, and that give me the idea of using an AND gate and not an NAND gate that the original circuit is having here. And the only chip that I have is 4081 pretty much. And I was looking when I was testing in the simulator. The simulator is excellent for showing you a little bit when you are playing with the circuit. It's showing you all these squares, blue and red squares, and you kind of you know from them when something is activated to positive and when something is activated to negative. And as you can see, everything is kept to positive here. It's keeping to positive already. But when I'm pressing this button here, the last one, it will bring to negative exactly as I'm pressing another reset button from there. So if I'm pressing this, it switched to negative, but it didn't work because it doesn't work here because I'm having this large 10 kilo. That's the problem. And I've resolved the problem. Why I keep it here, I don't know. Probably to for the movie, to show you on the movie, and it's still keeping it present. If I'm switching here or here, it doesn't doing anything. So it didn't work with 4081, but it worked with the discrete AND gate, which I built here. I built it with a discrete diode and a resistor. Way less more components than with an entire chip that is occupying a lot of useless space. And when I'm pressing this button, is activating. Everything is staying activated, which is interesting, but it's not resetting. As you see, it should have been reset. And if I'm pressing this button, it's not doing anything. But only when I'm pressing this button is resetting everything. It worked like this here in the simulator, but it didn't work like this in reality. Probably because of this 10 kilo. It might be. Oh, of course, this capacitor is doing absolutely nothing here. I didn't include it. Hmm. I wonder in reality. So this is the first working circuit that you've seen that I'm presenting on my breadboard here, on my other table. So these are the switches, and as you can see, this is a 700 ohms. And here, when I'm pressing this button, is resetting automatically all these other gates before, but keeping the last one alive. And when I'm pressing the reset, is resetting back to normal, and it's is functioning okay with this 700 ohms there. But when I tried with this guy here, it didn't work, if I remember right. And what I have on my table, on my breadboard there, I put every clock pin to positive, exactly as it is here. Exactly as it is here. And here, I try to create another circuit that is dealing with that last click. You will see in a second. So when I'm switching this clock and this clock, all those three, the first sector, the first module is activated. Also, all of these switches are linked to positive. Also, the clock is linked to positive as well, as it should be. This is the normal, and this is the correct way. This is the fourth circuit, and when I'm clicking this button here, is activating this clock here, this clock pin here. The output is activated as well, but then the AND gate is switching to ground everything, is resetting everything. So it's doing exactly the same thing as the original circuit did. And when I'm clicking again this button, nothing happens, nothing is clocking anymore. There is remaining stationary as the last only one click it needs. Is doing it automatically from one click. The first bounce that the button is doing is setting to high, and doesn't matter how many bounces is doing after that. It really doesn't matter, because this is locked into on state. And only this reset is actually resetting this fourth flip-flop, and the rest was already resetted, but the fourth flip-flop is resetted finally from this reset switch that I'm having here, as it should be only one reset button, pretty much, not two of them and weird shit, which I don't like. And here I did it with an AND chip, but I did try it after this. So this is the final circuit where that I built already, and it's very interesting. And this is the content. This is not really an AND gate. It's a binary bit that I used it once before in a project that failed, actually. But here it did its job brilliantly. And actually, this part here, this binary bit, it's the internal transistors or arrangement from this 4081 AND gate, what is having inside. Let me 81. All right. So let's see a little bit what this 4081 is having inside, and it's having a lot of shit, a lot of stuff, which is very hard to comprehend from the first. I believe, yeah. Okay. So this is pin 1 and pin 2. So this is the input, and here is the output on pin 3. Also, pin 4, 10, and 11 are the outputs, because it's having 4 of these. But this is the circuit diagram that is having. It's inverse from what I've built here. Here I built it with N-type transistor, and here is a P-type transistor on the bottom. But here is inverse. Let's see. Is a N-type of transistor. This is a MOSFET. This is a BJT transistor. But this is N-type. And here in my drawing is P-type, and this is P-type on the top, but here in my drawing is N-type. So I had to switch them because I was following a logic in my drawing here. But that's where I got the inspiration to use the binary bit, but not really, not completely or 100%. I was thinking on trying a binary bit before looking here. This gave me an impulse, like a kick in the butt, in the right direction, pretty much. This told me that I should try it. I should make another try with this configuration. Of course, I didn't use MOSFETs. I used BJTs, and I can use MOSFETs as well. No problem. But I did use it exactly as here with P-type in the top and N-type on the bottom, but it absolutely didn't work at all. So I had to get back to this arrangement that I'm having for the final version that is right now. And I tried it many ways until I figured it out. This is the thing with electronics. You don't try it one time and you give up. You try it 10, 100 times and don't give up. And continue trying until it makes sense, until you start to understand it, because this is like a language. You have to learn the words. I certainly don't know all the words in this language, but I know some, and I'm very consistent and insistent to it. I put 2 LEDs in the real circuit that I built to show me when is on one transistor and one is on the other transistor. Pretty much this 2 LEDs that I'm having here, this test LEDs that I'm having here, is telling me when one transistor is activated and when the other is deactivated. And this binary bit thing is having the role of a single gate from one single chip here. And it's very interesting to have it there because it's doing a very, very cool job. And I want to say it's easier to build it this way, but in reality, nothing is easy to build. It's a bit more complicated than I wished, but it's doing exactly the thing I wanted to do. That's the most important thing. So let's play it again. well, I don't know if I played this one. So this is the actual final circuit that I'm having right now here, and this is activated the start gate, and when I'm pressing this button, bang, is creating this switch here, and is telling me that this transistor, the PNP, switched, and this circuit, like before, is keeping the button only on one click, doesn't let it do the bouncing thing, and when I'm pressing this reset, as you can observe, is automatically reset all the pins on the three flip-flops module here, the first module. And when I'm pressing the reset switch here, is actually resetting the fourth one, the fourth flip-flop. Also is resetting this entire circuit module that I'm having here, which is a bistable flip-flop. I actually thought of it. Yeah, I was thinking on monostable flip-flop, and surprisingly didn't work with monostable. Actually, there is a version of monostable circuit. Let me actually show you. This is the monostable circuits, and it didn't work for some reason. And I didn't stay too much to try every permutation on it. Actually, this is also a single transistor. Monostable is doing exactly the same thing as the flip-flop version, but is using only one transistor. And I tried this as well, and surprisingly it didn't work. I really had to create a lot more circuitry around it, and it was hell. It was hell, and I couldn't do it. And then I got back to this bistable flip-flop, and I tried it, and it worked from the first try, and wow, that's it, that is it, this is it. And I was kind of having luck with this circuit. It worked from first try, almost. I had to be very careful which one is the output and which one is the input. As you can see on this line, I had to decide this is an input, and I also had to decide this is the output as well. It could have been any other points there, but I had to make a decision which is which, and it worked from of course logically, and I was thinking about it. I didn't put my finger there, it is, and it worked. It was a logical decision, but it was the right one. That's why I'm saying it was. I was lucky. I did make the correct decision, and okay, let me show you now the real circuit in reality. Hello everybody. And here it is, the final circuit with all the transistors with the binary bit thing, which is here. Let me make it like this. Let me actually look through the camera, and that's the one there. You see it there? And there's this metallic. I'm not sure if you can see it. Let me actually do it like this. So this metallic transistor there is the PNP, and the black one is the NPN. And is this in this configuration here? This is the PNP. That's the NPN. 1 kilo here. It was very important to have, and it's somewhere there. I believe that's the one there. And the two LEDs that I put them here on the paper, and also draw them on the circuit there. And this is the bistable flip-flop. And here it is, the flip-flop, bistable flip-flop that I'm having here. So this is a flip-flop, this is a flip-flop. So these are all three flip-flops, the fourth flip-flop, and the fifth flip-flop that I'm having. So a lot of flip-flops here. It's a flip-flop circuit, which is very, very interesting. I really like this project. But I don't think it worked with the AND gate. It worked for the preview circuit before this, but not for exactly this when I'm having this functionality. So let me show you the functionality right now. This LEDs, you see, when I'm pressing the reset, this is the reset button here on the top. This 1, 2, 3 are the setting, the clock, the three clock buttons for each flip-flop, and this is the fourth clock button that will operate this LED. If I'm pressing it right now, nothing happens. If I'm pressing this, guys, nothing happens. It must be in a special order. This is the master reset that will reset the fourth flip-flop, also resetting this entire discrete flip-flop, the bistable flip-flop made from discrete components that I'm having here, right here. Right. So this side is a discrete flip-flop, and these are integrated flip-flops. So let's make it. This is the reset that doesn't. When I'm pressing it, is switching. These two transistors are switched when I'm pressing one of the reset pin button here. Let's do it the clocking. And when I'm pressing here, it doesn't matter how fast or slow. And if I'm pressing all these other buttons, nothing works. But is remained in this stage. Everything is as in the simulator is deactivated. And when I'm pressing this reset, this is the actual reset. Only one single reset button for the fourth flip-flop, and is resetting. And this is signaling that is coming into the reset mode. And this is it. I'm doing it again. And it doesn't matter if I'm pressing it longer or shorter. Yeah. It doesn't matter if I'm pressing it multiple times. It will still remain activated. And only when I'm pressing the reset button is working. Of course, this circuit is not perfect. Probably it will switch weirdly. It will have some weird switching. But it is doing the logic that I wanted. That's the thing. And I'm not sure if it will work with another chip, another flip-flop chip. This instead of this discrete flip-flop that I'm having here, to have another chip, another flip-flop. I'm not sure if it will work. Browse. So it appears I have a problem, even with this guy. It's still switching by itself for some reason, huh? Very, very weird. Let's see. Is interesting. For a safety, as a safety precaution, no, you can add. So this is not used here. That button. As a safety precaution, is good to add a capacitor here to the ground of 10 microfarads, and probably here a capacitor also to the ground as well. 10 microfarads, probably. Let's see if I'm doing it. Just a precaution to be sure, absolutely sure, is stay locked. Sometimes I got some erroneous clicks, double click, from this button. Right now it's stable, but it's better to be sure than sorry. So pin 8. Uh-huh. There it is. Let's check it right now. 1, 2, 3, and 4. Oh yeah. Okay, come up. And it will stay like a motherfucker on and not switching automatically. Also this breadboard is not perfect. It's having some issues, so be careful about it. And it's very stable right now. It doesn't matter how many times I'm pressing this button. It's staying on the last bit there. Let's see if I'm doing that. And resetting. So I'm very happy about this circuit. I'm very happy. It was a challenge. It was a very good challenge. And if you like challenges like I do, try to make something similar. Adapt your IC integrated circuits that you have to this circuit, general circuit behavior that I'm having here, and see for yourself if you can find a way to use your flip-flops ICs. Even if it's made with discrete components like this, it's occupying quite a lot of space. But if the space is not a problem, you can get some quite to the point results using discrete components and modules like I'm having here. Very specific behavior you can get from using discrete components. That's the thing. And extremely customizable. You can tweak everything until you get the result that you want, and that's why I'm using. It's like C++. This is like C++ with discrete components, and using the chips, the IC is like using C#. That's the difference. And it's a bit harder and a bit longer code to write with discrete components, but you can get much more specific results and very interesting results than using only the chips themselves, which can fail you sometimes. But if you want a special wicked design, that's my method at least, and I'm combining the two worlds, the worlds of chips, of ICs, and the worlds of discrete tree components, and I'm getting where I want it. That's the point. All right, I really hope you like this little project of mine. Well, it wasn't absolutely my project. This project of mine, in the sense that is made with my chips, and half of the circuit, with a big chunk of the circuit, is my my circuit. Use it at your discretion. I don't really care. I'm just playing around, and yes, I hope you really like it. Leave a like if you watched my entire movie. Please leave a like, and thank you very much for watching, and see you later, I suppose. And that's it. Thank you very much. See you later. Bye bye.